Welcome everyone to our latest InterMET.digital webinar. Today's topic is about artificial intelligence and weather data and is the third in a planned series of webinars by InterMET.digital exploring the business opportunities of addressing the causes and impacts of weather and climate change. I'm Jan Dutton and I'm the CEO of Prescient Weather, the providers of Crop Profit and the World Climate Service. And I'm here today to host the webinar. Today, we will welcome 4 expert panelists. Sue Haupt is Deputy Director in the Research Applications Laboratory at the National Center for Atmospheric Research. Florian Pappenberger is the Director of Forecasts at the European Center for Medium Range Weather Forecasts. Amy McGovern is the Director of the NSF Artificial Intelligence Institute for research on trustworthy artificial intelligence in weather, climate, and coastal oceanography at the University of Oklahoma. And John Williams is Senior Manager in the Forecasting Sciences Division of the Weather Company. Each panelist will give a brief presentation, and when they're all finished, we'll move on to a panel discussion and audience question and answer period. We've had some questions in advance, but we're hoping that our audience will be thirsty for knowledge and look forward to receiving your questions via the Zoom question and answer capability. We'll be looking at these questions once our experts have finished their presentations. One final word, please bear with us if there are any technical glitches. So without further ado, let me introduce our first expert. Sue Haupt is an NCAR Senior Scientist and Deputy Director of the Research Applications Laboratory at the National Center for Atmospheric Research. She leads projects in the applications of artificial intelligence, renewable energy prediction, and coupling mesoscale to microscale models. She is also a contributing and founding director of the World Energy and Meteorology Council and a fellow of the American Meteorological Society. Sue, the floor is yours.
Thank you, Jan, for the nice introduction. Today I'm going to be talking about machine learning for weather and climate, emphasizing energy applications that we do at NCAR. So first of all, I wanted to make the point that AI, machine learning, is not new. It's been around for some time. And in fact, NCAR's first big success began in the 1990s with the Dynamic Integrated Forecast System, or Diecast. What Diecast is, it's a machine learning post-processor of model data where you bring in historic model data, historic observations that are matched with the data, you train Diecast, and then it's able to make forecasts for the future. So it basically optimizes the inputs, tunes it to the observations so that we get better forecasts. It enables decision support in a lot of areas. It uses real-time data, very much an Internet of Things application, large amounts of historical data, as well as real-time data from multiple models together with observations from multiple sites. Now, Diecast was originally developed in the late 1990s. It was part of a project in collaboration with the Weather Channel, now the Weather Company, part of IBM, and I think John will talk about their evolution a little bit later. It's used as the weather engine in a lot of our projects that include surface transportation, our PICA alert system, solar energy forecasting, wind energy forecasting, where I'll focus today, and precision agriculture, as well as it's licensed to various commercial forecasting companies. Now, Diecast is not static. We continue to improve the predictability using more modern methods than we applied in the 1990s. For instance, some recent advances are in terms of forecasting probability of precipitation. Here you can see Breyer's score, where a gradient boosted regression tree is able to outperform the standard bias correction that is part of Diecast. And in fact, over the very shorter time range, we see yet more improvements. So we're moving to train on more data by clustering data into climatic regions across the United States and elsewhere. Now, as mentioned, we use Diecast as part of a full systems approach to forecasting for renewable energy. An example here is a system we've recently stood up for the Kuwait Institute for Scientific Research, the Kuwait Renewable Energy Prediction System, or CREPS. Now, right at the centerpiece of CREPS is Diecast, where we bring in data from global models, from the US models, ECMWF, Canadian models, et cetera. We bring in very specialized observations from the renewable energy site. We run a very finely tuned version of WRF optimized to predict solar irradiance and wind speed. And we have very specialized observations right there at the site. So if you look at the system, it really does blend multiple physical models with the red encompassed AI models. So Diecast does our longer range type forecasting, but we often find that standalone AI methods are better for the very short range forecasting for both wind and solar. In addition, a lot of the operators really do like having probabilistic information. For that, we apply an analog ensemble approach with a Shockey shuffle when we want to combine probabilistic information from wind and solar at the same time. Now, just an example of our short range forecasting systems using AI, for instance, Diecast Solar uses a model regression tree, and in particular, the Cubist implementation of that. And we train on data on the order of a year, and we find that when we compare the Cubist, the purple line here on the left, to the Diecast already optimized version based on the NWP, it actually performs yet better. Both are better after the first hour when compared to a smart persistence that allows a change of the solar angle without having a change in cloud cover or aerosol content. Now, the plot on the right shows the percentage of improvement of this method over Diecast for the first 6 hours. And we see at time 0, there's as much as a 50% improvement, and then it levels off to on the order of a 10% improvement over the longer periods. Now, I mentioned that we use an analog ensemble approach for probabilistic prediction. It saves a lot of computer time by using this AI method rather than running large-scale ensembles. So the concept here of the analog ensemble is you have today's forecast. You look over a historical record for similar or most analogous forecasts. You choose the verifying observations for those analogous forecasts and form a probability density function of that. The mean of that PDF then becomes your improved forecast, and the distribution itself provides the probabilistic information. Now, one advantage of the analog ensemble that we have applied, for instance, in the Kuwait system, is even though you may be forecasting wind speed or irradiance, you can use verifying observations of actual power output. And in fact, we find that does improve our power output prediction, which is the variable that the client has the interest in. So we use this for both solar and for wind power output. And here we see that even compared to Diecast, our very finely resolved system, that the analog ensemble trained on top of the Diecast forecast makes yet a better improvement. But in addition, it provides flow-dependent probabilistic information as well. And in this case, we combine the probabilities for wind and solar using a reordering technique known as the Shockey shuffle. Now, because this webinar is advertised as climate as well as weather applications, I want to look at how we use some machine learning methods also in the climatic realm. Staying with the energy example, let's look at what we can say about how the wind speed is likely to change across the United States under future climate conditions and its variability. So we begin with a high resolution, high quality reanalysis of current climate, where we're able to calculate means, variability, standard deviations, all the statistics. For the current climate, then we're able to calculate self-organizing maps. And in this case, we've chosen to use 24 SOMs to represent the patterns well that we found in the data. Now, because we've calculated the SOMs on this assimilated reanalysis data, we're then able to project onto current climate, downscaled climate model information. And we looked at various GCM, RCM, downscaled climate information, chose the CRMC/CCSM for combination as being the closest match to what we had in our original reanalysis database. Now, I'm not going to go through the whole complex technique, but then because we've matched the current climate, we're able to select future climate conditions. And in fact, we do a Monte Carlo sampling of the SOMs. We apply a climate change adjustment factor that was calculated more as a trend and come up with a proxy future climate of the resource variability. And in this way, we're able to produce maps of various regions sliced and diced by time of day and time of year. And what we found was it predicted that the change in the frequency of patterns is on the order of about 10%. Some places you can see 20%. You can see differences in the region this is plotting the expected change in wind speed between 1995 and 2060 for morning time periods. You can see the regional differences, the differences in the season. And we're able to calculate this because, and do an apples to apples comparison because we use the SOM technique. So in summary, I want to point out that machine learning is not new, but now it's becoming an extremely useful tool for applications in both weather forecasting and deriving detailed information from climate simulations. It's becoming a necessary component if you want to apply best practices for forecasting for specific applications. But that doesn't mean we can necessarily throw out our physics approach, our numerical weather prediction. That's a very important basis to using the AI. So blending the two is where I see the solution. And the idea is that we can advance applications of weather and climate forecasting through the systems approach that blends the physical approach with the machine learning. Thank you.
Great, thanks, Sue. I'm sure we'll be returning to some of the great points you've raised. But now let me introduce our next expert, Florian Pappenberger. Florian leads the forecast department at the European Center for Medium Range Weather Forecasts. The forecast department has a strong customer focus and is responsible for the 24/7 production of weather forecasts, forecast quality control, the development of novel forecast products, and the applications of those products to areas such as flooding, drought, fire, and health forecasts. Today, Florian is talking about the ECMWS new artificial intelligence roadmap and what it holds out for the organization's customers. Florian, over to you.
Thank you very much. And thank you very much for everybody for listening. I'm going to take you a bit more upstream now from what we just heard from Sue. I'm just going to quick introduction. Most of you probably will know who joined this talk. ECMWF is the European Weather Center, an intergovernment organization created by a group of European nations with the real simple mission to improve numerical weather predictions at the medium and long range. The main idea at the creation of ECMWF, and the reason why I'm repeating that is because I think it's also important then when we talk about AI, is to really push the limits of predictability, to work together through collaboration. Of course, when ECMWF created, that was a long time ago, nearly in the early 70s, the predicting range was 2 to 3 days. We're now aiming for 10 and more. And we're really trying to work together and trying to push this out. As already mentioned, what I'm going to do today is that ECMWF has a 10-year strategy, which just got renewed this year. And part of this 10-year strategy, we developed a machine learning roadmap. I'm going to give you now a brief version of this machine learning roadmap. And I'm going to try to do this by taking you through the forecasting value chain. So I'm coming all the way from the left-hand side from observations to a picture which is supposed to demonstrate to be data simulation, to a model, to an application, to an Earth system where people then use it. And in the background, you see of lurking a computer. Okay, all is of course based on big computers. Just to connect back to what actually Sue had to say is, and I think she was very right, there's a long-standing relationship between machine learning and methodology. It's not really a new one. The word may be new, and the concepts of scientists using machine learning tools or extract information to train and verify tools and how they apply to data have been there for decades. I've just picked out here 3 examples. On the right-hand side, you saw a bit what Sue had with her Diecast, at least if my interpretation is totally correct, which is sort of the post-processing using methodology as input or forecasting as input as part of making better tools for users. But also on the left-hand side, we always had huge amounts of observations. We had observations in a volume which we could never handle manually, which we always had to do automatic checking. We always had to do quality control. We always had to do filtering. We always had to use advanced statistical techniques to actually use them. Then data simulation itself. If you really think about it, at ECMWF, we use something which is called 4D VAR. I think if you actually sort of extrapolate it slightly, you could argue in a reasonable point, this is actually something which is sort of very akin to machine learning and artificial intelligence. So really, the question is, where do we go from there? Just saying it's something which has happened wouldn't really make a very good story for a new strategy based on machine learning. And we really, at ECMWF, thought very hard about this. And how can we use this new machine learning tools in a sort of holistic approach in the entire weather prediction chain? I admit this is a simplified weather prediction chain, but I think it does for this talk. Weather and climate science and operation is always part of big data nowadays. Observations are in the hundreds of millions. Our model includes over 2 million lines of code, and the products we currently disseminate, you measure in tens of terabytes. So building on this experience, which we really gained over the last decades of using versions of machine learning, our vision was really to unleash the power of modern machine learning tools. Sue has presented some of them. Others would be deep neural networks, which I know are going to be shown later by, I think, John, if I remember correctly, or Amy. But also really to see where can we use this machine learning in the entire workflow. There's one thing I sort of want to start with, which I find quite important in our strategy or in our roadmap. And I think it's really the human dimension of such an ambition. It's maybe a bit a paradox because machine learning and humans sort of, seems to be a bit difficult here. But really, we thought that the only way to really embed machine learning into an infrastructure such as a forecast model at ECMWF is to train people and scientists up to use them in the most optimal way to actually go further. And I know that Amy will pick up some of that in one of her slides later. Weather prediction is a lot about modern technology. Satellites and supercomputers are the most obvious ones to mention. And in a way, we're quite working already closely with space agencies, and we use the instruments in all this way. We use big computers, and we really work on future computing architecture to meet our needs of science. And this is all part of a normal training at a weather center. And of course, machine learning is just another dimension of that. So machine learning has to be intrinsically part of your scientific culture inside your organization. Let's just pick a few examples in practice. what do I mean by embedding it into a forecasting chain, a forecasting value chain? I think I sort of already started with observations. That's sort of the easy bit here. When we're looking at the future, machine learning will be used for contributing to screening observations and filtering observations and understanding observations, which we're going to collect from all sorts of devices. Any IoT device you can think of. Think of a car, a mobile phone, or your personal weather station if you're a proper geek in your backyard. These will be going into a forecast engine. We will be using them. And for that, we will use machine learning to actually be able to use them. We need them quality controlled. I'm not going to talk about data assimilation because I sort of covered it slightly. Just to go to the other dimension, which is the model itself. If you think of the model, where do we use machine learning there? Well, a very simple approach, or one simple example would be to replace expensive physical algorithms that we currently have in our code and run them cheaper. Simple example would be a radiation scheme. Can we replace a radiation scheme with a machine learning scheme, make our computer can our code much quicker, and therefore produce better forecasts? And then, of course, goes all to the right-hand side, which is really the post-processing application in terms of using different types of information in that. I sort of excluded one really important bit here. All of that is only possible, is currently so dominant, is because we have infrastructure which is really tailored to machine learning. And I said this computer is lurking in the background. It's not just lurking in the background, it's actually everywhere. Without a mix of, let's say, GPUs and CPUs and any other type of new process, we couldn't even do what we're trying to do here. So that is actually quite important. So this was really a very, very brief whiz through the elements of a forecast. And I just want to demonstrate you where different, or exemplify where machine learning sort of becomes part, or could become part, of a production of forecast in that sense. It will take different roles, and we will have to use different methods, meaning that we need to find the right machine learning tool for the right job. There's quite a lot of them out there. Not all of them will always fit, and that will be a huge part of our workload too. Having said that, I already said that we have a strategy. We've got a machine learning roadmap. We've published that in great detail, and I'm going to put on the chat also a very extended version of this talk. Weather and climate predictions, I hope we all agree, are complex with many components, producing a huge amount of data, usually on the world's largest supercomputers. In short, it is a discipline which is perfect for machine learning and AI, and it can in turn, of course, massively benefit from that amount of technology. The main point I really wanted to make today is to describe your pathway, to describe you how I see machine learning as a part of a producing engine of forecast. In a way, this is still a dream. This is where we want to go. We have a roadmap. We have a roadmap with very detailed milestones in them where we want to go in the next decade. We really can't do this alone. It's very clear that we will need experts. Many of the experts are in this room and around this table now to actually make this happen. It's a huge job. It has to be done collaboratively, and only together we can really achieve this. And I think with that, I sort of want to end because there we are.
Great. Well, thank you very much, Florian. Your talk certainly highlights one of the things that I've started saying over the past couple of years, which is that meteorology is the original big data science. And I think your talk highlights that very nicely. So next, I'd like to introduce Amy McGovern. Amy leads the National Science Foundation Artificial Intelligence Institute for Research on Trustworthy AI in Weather, Climate, and Coastal Oceanography at the University of Oklahoma. Much of her current work focuses on weather analytics and physical data science, where along with her students, she's developing ways of applying artificial intelligence techniques to high impact weather phenomena, including tornadoes, hail, severe wind events, flooding, drought, and aircraft turbulence. Amy, take it away.
I'm not sure where you grabbed that sentence from, but that's great because the aircraft turbulence is actually work that was with John. So it is leads right into talking with John. So I was asked to talk, okay, all the computers have been working great for everybody but me. I was asked to talk about our new NSF AI Institute. And so I'm just gonna jump right into it. And all the people are on top of the slide, so I can't actually use my mouse. Here we go. Okay, so we are the NSF AI Institute for Research on Trustworthy AI in Weather, Climate, and Coastal Oceanography. And I've given a bunch of talks on this, so if you want the long version of it, you can look online. There was an AMS talk that was 25 minutes. This is the short, like 5-minute version. So it's just an overview of what we're doing. I wanted to highlight all of our partners. On this slide, starting at the top right corner, OU is the lead institution, and then we have 7 universities, so Texas A&M, Corpus Christi, North Carolina State University, Colorado State University, University of Albany, University of Washington, and Del Mar College, which is a community college, and they're part of our broadening participation plan. And then we're partnering with NOAA and with NCAR, so where SUE is, it's a federally funded research center. And we have 4 private industry partners: Google, IBM, Disaster Tech, and NVIDIA. And in fact, John is one of our partners. So I have a slide that's going to lead right into his slides. And if you want to learn more about us, we have both a website and a Twitter handle, although I have not yet tweeted a lot, but I'm getting there. I'm the one who runs the Twitter handle. But the goal of what we're doing in our institute, and our short version of our name, by the way, is AI2ES, for AI for environmental science, is that we will uniquely benefit humanity by developing novel, physically based AI techniques that are demonstrated to be trustworthy and will directly improve prediction, understanding, and communication of high impact environmental hazards. So I'm going to briefly, if my slides behave, I'm going to very, very briefly talk about it. We have 4 focus areas for our research. First, we have foundational research in trustworthy AI and machine learning, and I have like one overview slide on that. We have use-inspired research in environmental science, so a variety of environmental science hazards. I have a couple of slides on that. We have foundational research in risk communication. Because we were given a short time limit, I don't have any slides on that, but what I want to tell you is that the social science aspect really, really matters. If you look at this graphic here, we have the AI, we have the environmental science, but we are working with the risk communication researchers hand in hand so that they actually inform us to tell us what it means to be trustworthy. And then the 4th focus that, again, I didn't have time to have a slide on, is on our workforce development and broadening participation plans, but I'd be glad to talk about it through questions, or you can look on our website as well. So looking at the foundational research in trustworthy AI and machine learning, we have 3 goals. The first is that we want to develop explainable AI methods that are aligned with environmental science domain perspective and priorities. And what does that mean? It means that, sort of what Florian said right at the end, that weather data is sort of the original big data. Weather data is different than what traditional AI researchers tend to study. They tend to study, as probably you've seen, lots and lots of images, for example, and IID data, independent identically distributed data. Weather violates every assumption that comes along. It's autocorrelated in space and time. It's not just images. There's high amounts of information in a field, not just an individual pixel. You can't say this pixel belongs to a panda, which a little bit you can't do in images either. But with weather data, you really care about everything that's around you, and you care about time. So we need to develop our explainable AI methods that align with all of those important needs of the data. And so I have an example in the upper right here from some work we've done on some hail prediction. But again, for the matter of time, I'm just leaving the examples there. The second goal is that we want to develop physically based AI techniques for the environmental science domain. And that is, what I mean by physically based is that we care about the rules of physics. We care about the laws of physics. We want the laws of physics to be respected. When your AI does the right thing, that's great. When your AI does the wrong thing, you'd like your AI to do the wrong thing in a way that's plausible. And you'd like it to not be that wrong, frankly, but that's just a different matter. You'd like it to at least be physically wrong. There was an example we have where, when we were doing a tutorial of something where it predicted that something was, normal temperatures, and then all of a sudden it was hotter than the surface of the sun. Not physically plausible. You need your AI to fail realistically. The third goal is to develop robust AI prediction techniques, and then validate theoretically and empirically their performance. And one of the things I want to point out with that goal, this actually goes with the second graphic here, is that when you're doing traditional AI research, you often talk about an adversary, and an adversary that is corrupting your data. Weather, along with being the original big data, also provides its own adversaries. The extreme events are adversarial events. And if you don't make your AI robust to both extremes that are valid and extremes that might be invalid, you need to throw out, then your AI is not going to produce physically plausible results. So the graphic I have there is from something called the Oklahoma Mesonet, which is a surface-based observation system in Oklahoma where they take measurements every 5 minutes across the whole state. They've been doing this for 25 years. It's a fabulous data set if anybody's looking for some data to get started with. But this is from a particular event where, it was pretty windy that day. These are in miles per hour. But it was really windy in one spot. It was 151 miles an hour. And you need to make sure that your AI both understands that that's a valid measurement and that it's robust and not doing something crazy to the other areas around it because it's got that measurement. So we're doing the foundational research in AI. We are doing it hand in hand with the different meteorologists and atmospheric scientists and ocean scientists. And so our use-inspired research, we have 5 areas of use-inspired research. And again, for the matter of time, I'm going quickly. So the first one, the 2 goals for all of these areas are that we want to be able to provide actionable information and improve both our understanding and our prediction of the phenomena. So we're looking at convective weather. So I have a graphic there from doing tornado prediction in the next hour and using XAI to understand what it has identified. We're looking at winter weather. I wish I had a graphic from the most recent storm. This is from an older storm, but you know, winter weather provides a huge impact. And if we can create AI that is trustworthy and used by our end users, we can significantly improve both the predictions and the environmental impact. And I'll give you an example of that. If you have a better prediction system, you can use less salt on the roads, which then has a corresponding downstream environmental impact. Our third use-inspired research area is tropical cyclones. Here we're using AI. You know, the example I have here is using AI to improve our understanding of the formation and the rapid intensification of the tropical cyclone. So trying to take, for example, use an AI system to take a polar orbiting satellite that's only available a few times a day and train an AI system to mimic that using the geostationary satellite that's available much more frequently. So then we can have more data available that we can then use to improve our predictions. The fourth application domain is looking at S2S, which is subseasonal to seasonal prediction. So in the 2-week to 2-month time frame specifically for what we're doing. And we want to specifically focus on extreme weather and whether or not we can improve our prediction and understanding of what's going on for extreme weather events, such as very large rainfalls, atmospheric rivers. Can we figure out what's going on that's causing those events and what's relevant? And so this is an example of a region that is relevant for the machine learning prediction of extreme rainfall over California, North America area, but California region specifically, 18 days later. And you'll note that's not North America, that's Asia, because what matters 18 days in advance is Asia. The fifth domain is coastal oceanography. And here we have a lot of applications that we're looking at. Ocean eddies in the Gulf of Mexico, which are basically very large scale rotations. They're not like tornadoes because they are very different in space and time, but we still need to be able to predict them because they have high impact, particularly on the oil wells that are out there. Harmful algal blooms, which are harming the entire bio-eco-cycle. Compound flooding. One that I'm going to talk about on the next slide, which is cold stunnings, which just happened last week. Coastal fog prediction, and somehow I managed to put flooding on there twice when I was combining 2 slides. So we're doing flooding twice apparently. So this is a slide to lead into John, actually, because this is a collaboration with IBM. So those of you who may have been reading, if you're not in the Midwest, you may have just been seeing this in the news. We experienced an extremely large cold event. It was extreme in all ways. It was very cold. It was -10 here a week ago, and today it's 70. It's a little crazy. But then during this cold stunning event, what happens is the water gets cold enough in the Gulf of Mexico. Specifically, this particular event is in the Laguna Madre, where the turtles, as you can see a turtle in the lower right-hand picture, the turtles, they get cold and they do something called cold stunning. They float up to the surface and then the ships run them over and they kill them. And we don't like that. And so what we have is we have an AI model that's predicting the cold stunning events, and then we have agreements to stop the traffic so that the turtles can be saved. And this is turning out to be twice as large as the previous largest cold stunning event. They're estimating right now 10,000 turtles were stunned. And IBM is part of the group that is, along with Texas A&M, Corpus Christi, that are doing these predictions of the cold stunning events, because you don't want to just stop traffic willy-nilly. You want your AI to be trustworthy because you want to only stop traffic when it really matters. Oh, I thought I hadn't put this in. I will talk, for the matter of time, I will say that I'm probably out of time, and I would be glad to talk about workforce development and broadening participation in the questions. I just want to say we are developing a community college level curriculum for AI, and we'll be sharing that nationwide. And it's aimed specifically at improving our diversity in both AI and environmental science. We also have a lot of resources for workforce retraining on our website. So this is my last slide. I'm going to end here and say that, you know, AI can really help us to be resilient to climate change. And climate change and environmental science are wicked problems. They're the original big data. They're all the other things we've been saying. We have a vision of long-term funding and working across academia, government, private industry, NGOs, international, working across everybody so that we can apply AI to both weather and climate change so that we can be more resilient as the climate is changing. And I will stop there.
Great, thank you very much, Amy. I have to say, those are some pretty interesting and meaningful applications that you just shared with us as a result of using artificial intelligence to improve the science. Thank you very much for that. Our next and final expert is John Williams, who's very well placed to give a private sector perspective on the growing importance of applying artificial intelligence to weather data in meteorology. As senior scientist, machine learning, and senior manager, forecasting sciences at the weather company, John leads a team of scientists and software engineers who use AI and data science in conjunction with meteorological expertise to create and verify state-of-the-art weather forecasts for a variety of businesses and individuals around the world. So to conclude today's expert presentations, here's John Williams.
Thank you very much, Jan, and good morning, good afternoon, good evening, everyone. It's a real pleasure to have the opportunity to participate in this panel today with my impressive colleagues. So I'd like to take a few minutes to speak about how AI helps us at the weather company and IBM Business forecast weather, a lot of the elements you've already heard, and also how it helps drive business value from those forecasts. So as you've heard from Sue and Florian already, and Amy, AI has been used in weather forecasting for many decades. But recently, the number and resolution of models and sensors has really exploded the amount of available data, making it essential to use automated tools like artificial intelligence to use it all effectively and derive value from it. The Internet of Things has also increased the reach of observations from personal weather stations and connected vehicles to cell phone measurements of pressure, which we can use in our models. AI is a key tool for performing quality control, throwing out bad observations, and extracting relevant features. As Florian mentioned, in numerical weather prediction, machine learning is being used to optimize parameters and accelerate runtimes by replacing some physics modules. These advances are relevant to IBM's own numerical weather prediction modeling as we run an hourly updating global convective allowing model called the Global High Resolution Atmospheric Forecast, or GRAPH. AI is also particularly powerful for learning how to fuse data from multiple sources, as Amy showed a lot of different examples of this. For example, creating nowcasts from a combination of numerical weather prediction model data and the latest observations from radar, satellite, or surface stations, some of which may not have an obvious or well-defined physical connection to the variable being forecast, as we see in several of the applications Amy spoke about. And one she mentioned was turbulence, where a lot of the data that we have doesn't really relate to the turbulence at aircraft scales, and we have to infer it using machine learning models. And as Sue mentioned, AI is important for deriving hyperlocal relevant forecasts from an ensemble of numerical weather prediction data and other sources by learning intelligent downscaling, systematic error correction, and optimal blending to create deterministic and probabilistic forecasts. And she also mentioned using the Shockey Shuffle. At IBM, we have our version of that, using these methods to create weather scenario forecasts. Or you can think of those as probabilistically calibrated ensembles. So the strength of AI is that it is fast and untiring, so it can make use of the latest data almost immediately. But AI can still be challenged in unusual, rare, or extreme situations not well represented in the training set. So for that reason, the weather company employs an augmented intelligence approach with human forecasters over the loop, watching the automated AI forecast and occasionally creating filters over selected regions that nudge the forecast or put on guardrails to keep it within certain bounds. Or they can even add text that helps describe the impact of an event. So when you see the forecast of the Weather Channel app or weather.com or on IBM's operations dashboard for businesses, it has the advantage of this extra layer of human expertise augmenting the artificial intelligence. So that's a little bit about how AI helps create the forecast. Now, how does AI help us drive value from the weather? So let's think in terms of customer persona. Who are they and what problem are they trying to solve? So for instance, you may be a parent wondering how to dress your child for school so that they're comfortable and safe and able to participate in recess. Or an airline wondering whether to proactively delay or cancel tomorrow's flights in the face of weather conditions that may impact landing capacity. Or perhaps you're a farmer facing a near freezing forecast and needing to decide whether to deploy expensive blowers or misters to help protect your crop from damage. To help inform these decisions, we use a decision paradigm with 4 parts. First, we ask, what could the weather be? Second, how do the potential weather scenarios, coupled with the actions you might take, translate into impacts you care about? Third, what is the value of each of these possible impacts? And finally, what is the action that maximizes your expected value? That is, maximize your profit or minimize your loss. For the farmer facing a potential freeze, suppose the forecast gives a 20% chance of freezing weather and an 80% chance of not freezing. The farmer can either take an action to mitigate the impact of a freeze or not take any action. In this example, mitigation costs $1,000, but saves the crop if it does freeze. And not mitigating costs nothing, but risks crop damage of $10,000. The expected value of each action is calculated by taking the product of the probability of freezing times the impact value of freezing, plus the probability of not freezing times the impact of not freezing, which is a loss of $1,000 for mitigating and $2,000 for not mitigating in this case. So in this case, the optimal action is to mitigate because the potential crop loss is high, even though the probability of freezing is only 20%. Now, of course, the analysis I just presented was dramatically simplified. For one thing, more than just the temperature matters. The temperature, relative humidity, precipitation, and wind, for instance, all determine whether the crop will freeze and how effective the blowers and misters would be. So instead, let's look at how to solve the problem if we have a large set of representative forecast weather scenarios, defining all of those variables that matter. Each weather scenario, coupled with your choice of action, yields an impact to your crop. It also determines how your neighbor's crops will fare, and therefore influences what the value of your crop would be at harvest time. Those factors determine an impact value for each combination of weather scenario and action, and we can once again compute the expected value of each action. Here, it's just an average of each column if we assume that the scenarios have been created to be equally likely. In this approach, an artificial intelligence and machine learning algorithm, or even a physical or heuristic model, can be used to predict the impact of the weather on the crop and the crop price. The farmer should choose the action with the highest expected value. She can also look at the risk, the probability of losing more money than she can afford, and choose the optimal action under that constraint. So the combination of weather data and AI has a wide range of business applications. For instance, it can help optimize supply chains, help businesses recognize opportunities to engage their customers, build their brand, optimize store operations by predicting what customers will want to buy and when, and a wide range of risk and financial management applications. They can help businesses schedule their weather impacted operations and give them the situational awareness to stay safe when working outside. They can predict power outages and help utilities pre-position crews to help minimize disruption. And they can help predict crop yields and hence commodity prices. And I think there are many, many more applications to come as weather data, cloud computing, and AI tools become ever more accessible and accurate. So to wrap up, here are 4 things I hope you'll take away from this talk. At the Weather Company and IBM Business, AI helps create timely weather forecasts and current condition analyses with humans over the loop. AI can be used to learn and model relationships between weather impacts and their economic value. A set of representative weather forecast scenarios and impact models can facilitate decision optimization, which can move the weather enterprise beyond decision support, which we've often talked about, to the potentially much higher value domain of decision services. And finally, a little plug for my employer. IBM offers a number of industry-specific weather solutions and also facilitates the ability of partners and customers to develop their own weather applications via a rich set of data APIs and a hybrid multi-cloud platform built on Red Hat Enterprise Linux and OpenShift. And with that, thanks very much for your attention. I'll turn it back over to Jan.
Great, thanks very much, John. And thank you to our other panelists for your invaluable insights. So we're now going to transition to the question and answer period. And I'll just point out that at the bottom of your Zoom application, there's a little button for Q&A, and you can ask your questions there. And the panel will do their best to answer the questions that we receive. So John, since you were just speaking, I'll ask you the first question. Right at the end there, you mentioned using representative scenario forecasts to help with the decision context. Can you talk a little bit about how those are created?
Yeah, thanks, Jan. What we do is we take the vast array of forecast data that we have, including the great ensembles created by ECMWF, and we apply machine learning tools to calibrate those probabilistically to observations. So things like Bayesian model averaging, logistic regression even. And once we have those calibrated probabilities, we can draw scenarios out of those using a method called ensemble copula coupling, which is like the Shockey shuffle technique that Sue talked about. So that we actually come up with these scenarios that are both physically reasonable, feasible, but also consistent with our calibrated probabilities.
Very interesting. All right. Thank you very much. So a question came in, and I will address this to Florian, since you have just completed a 10-year strategy review. Can you give a summary of where you see artificial intelligence going in terms of the atmospheric sciences and meteorology over the next 10 to 20 years?
It's a very good question. 10 to 20 years is quite a long time in the future. I'm sure we're going to have something else in between. But I think we do see really AI and ML as being intrinsically becoming part of the forecasting chain in many aspects. I don't think it will work everywhere. And the thing which I think Sue said at the end, I think is uttermost true. We will not be able to throw away our physically based or dynamical models. They always will be part of it. And we will be sort of approximating or using AI wherever it's appropriate for this particular thing. So I think if you're asking me where it will be in 10 to 15 years, I think it will just be everywhere, similar as we use now computing tools and programming languages as such. We do have a very detailed point-by-point answer to this one, which is in this roadmap, but I'm not going to bore you with that. I think it's better if you just read it. And then I think Sue had a very good answer to that too.
Yeah, Sue, would you like to answer?
Could I add to that? We showed these forecast correction techniques and post-processing techniques, and most of them so far has focused on correcting at points. But we know that the weather doesn't necessarily move point-wise. It deforms, it elongates. There's a lot of, oftentimes we have systems and there's a phase shift issue. One thing I see deep learning doing in the near future is being able to actually identify features, phase shift them, and do really spatial temporal corrections in a different way than we've been able to do in the past. I know John and Amy worked in spatial temporal corrections for a while too.
Great. Another question that comes in, again, John, you mentioned decision services. Can you talk a little bit more about what you mean by decision services?
Yeah, I think we think in terms of a value chain where we go from sort of the fundamental data into the impacts and then finally into the decisions. And the data by themselves, if we don't process them, they're not particularly valuable because you have to be an expert to understand them. So to make them actually accessible to people, you need to translate them into impacts that they care about. And then if we can go that extra mile and actually help people figure out what the optimal decision is to make based on the weather data, based on these weather scenarios, then we're adding sort of the most value that we possibly can. So I think as a weather enterprise, we're moving from the left to the right in that weather value chain.
Great. So yeah, it relates to another thing that I say a lot based on my experience in the industry, which is that weather data has no value until you enable decisions from them. And so our role as experts in the field is to make decisions happen based on basically all of the observational data sources and forecast sources that Florian talked about. Great, thank you very much. Here is an interesting question, and I'll be honest, I'm not sure who should address it, but do you know if there are any plans or how national forecast agencies might be able to or start integrating AI?
I mean, we're working closely with NOAA, but I can't give answers for, maybe Florian answers for ECMWF and we answer, but yeah. Our center is working closely with NOAA. NOAA is working on creating a NOAA Center for AI as well. It was appropriated in the last budget, but not yet funded because that's the way the United States works. There'll be another round of funding for it, but they are already doing AI and they are working hard to integrate additional AI, and we are partnering with them a lot for both the research to operations as well as some of the workforce retraining.
Great.
And I would say IBM, our forecasts are fundamentally global. So if you take your Weather Channel app, to India, you'll get fundamentally the same experience that you get here. So we do try to serve the globe. In terms of individual governments, I know we have some collaborations, but I can't characterize them in general. And, and of course, the idea of the cloud and all the AI tools that are becoming available really does lower the barrier to entry. So I think, a lot of countries that may have found it too expensive to really develop their own services now may have a much cheaper route to doing that.
Right. So I'm curious, Florian.
This weather service is already implementing AI post-processing as part of their system.
Great.
So I don't think you see AI already all our types of downstream applications. I've just posted an answer to the COVID-19 question in terms of spread and where AI is used, for example. Very topical, it's used quite a lot. And we see this the same in extremes, floods, fires. You see it popping up everywhere at the moment, which is because, as John pointed out, computing infrastructure became more affordable and tools became easier to use, data became more integrated. So I think there's a real nexus now where you can start really having it everywhere and becomes available to most people.
Right.
I will say that the person who asked the question clarified that they specifically wanted to talk about developing countries as well, which, because we kind of gave an answer for not developing countries, but I think maybe John's answer is the closest, which is that they're working on a global model. And I know that some of the private industry like Google and IBM are working on, and Microsoft, they're working on AI applications in more developing countries. I've seen them talk about doing flood forecasting in India and Bangladesh, other countries. So maybe John can give a better answer to that as well.
I think that's right. One of the motivations to do our global convective allowing model was to extend the capability that we have in the US from the high resolution rapid refresh run by INSEP, so that it would also run in India, it would run in other places in the world and give them that same kind of information. And of course, that data is available through your app, but it's also available to train your models and build impact models and decision services on.
Great. And I do want to point out that AI is much more accessible than it was 10, 15 years ago. There's a lot of packages out there and a lot of tutorials where folks can learn it, online tutorials, excellent ones. They're, especially in our virtual world, there have been summer schools such as the one we held at NCAR about how to use AI, how to employ it, as well as how to, even having a hackathon where people could do it in real time. And I think Amy's center plans to continue to do things like that.
Great. And so a related question is, so you guys have discussed a little bit the computing resources necessary to achieve some AI goals. And I'm just wondering can you discuss maybe if someone was starting from scratch, what are the kind of investments that would be necessary to become proficient in applying artificial intelligence to meteorology and oceanography?
Who wants to tackle?
Amy, I think that one's for you, workforce development.
Okay, well, that's fine. I was in the middle of typing an answer to a question that hadn't gotten asked out loud yet. So how to get started, we are putting a lot of workforce development materials online. There have been summer schools for the last few years as well. So David Gagne from NCAR held a summer school AI for Earth last year, and it is linked on our website. I'm teaching, actually the question I was working on asking, I think Florian's also answering. I'm teaching an AI and ethics and geoethics course this semester. All of that is online. We will have a bunch more courses online. We, as the Institute, are teaching a summer school this year, and I know a bunch of you are going to now ask how you sign up. I promise when we have the details out, we will have them out very soon. It'll be in the next week or two, but it's at the end of July. That's as much details as I have. You can't sign up yet, but we're going to be doing summer schools. We're going to be doing short courses. All of the materials are going to be online on our webpage. It certainly is part of our mission. NSF's mission involves education, and thus it is part of our mission as educators.
Great, thank you very much.
And I'll add, IBM has a whole set of freely available tools too. You can go and you can get certificates. So check out IBM.com.
Great. So we have reached the top of the hour, and I think we should wrap it up. And so again, I will thank the panelists for your time and for your comments and your excellent presentations. We hope that everyone that participated and attended found useful insights into the enormous potential of artificial intelligence when it comes to applying them to weather data, climate data, and oceanography. And we just want to let everyone know that there will be a recording of the webinar available in the next few days, and we'll notify everyone who registered when it's available. So with that, thank you very much to the panelists, and we hope to see you on the next webinar, which we will be announcing what the subject is very soon, and that webinar will take place in March. And finally, if you have any questions that we did not answer, you can email them to ian@mediageneration.co.uk, and that information will appear on the screen as well. And with that, thank you very much. Thank you.